Hello and welcome to the Daily Space. I am your host, Dr. Pamela Gay, and I am here to put science in your brains. There's a whole lot about astronomy that is simply luck. This is why Beth likes planets. For the most part, they just don't do anything quickly. And exceptions like earthquakes can be detected from far away. So as long as you're looking from somewhere on the planet, you're going to catch the action. The sky. It is big. Stars and such are super tiny. This means on any given night, billions of things that go flicker or flare, or that just happen to be moving. Billions of things get missed as astronomers just happen to be looking in other places. But occasionally, we do get lucky. The Kepler mission, which was designed to find planets around alien stars, looked at the same part of the sky night after night, week after week, just waiting for the passage of a planet in front of its star. Kepler collected way more data than is used by those planet hunters, and astronomers continue to pour through the data looking for other astronomical phenomena hiding among the orbiting planets. And in a new paper that will appear in monthly notices of the Royal Astronomical Society, astronomers have found a massive yellow star that went from hanging out being a massive yellow star to exploding as a supernova, all in front of Kepler's cameras. Stars like this live for millions and millions of years, and the entire pre-explosion warm-up act only lasts days. And it had never before been seen. Now, thanks to Kepler, we have 40 days of data covering this entire event in amazing image-by-image stop-action detail. This work is led by Patrick Armstrong, who states, "We've always missed the very, very start of a supernova because it is so exceedingly difficult to capture that. Normally, we spot supernova when they are at or near the brightest part of their explosion. This data allowed researchers to instead catch the timing of an early shock wave moving through the atmosphere and signaling the start of the star's collapse and explosion. This work can be used to constrain existing supernova models and answer questions like, how do stars die? And what elements do different stars make? One star may not seem like a lot, but in this case, one star is the only star we've seen, and it will be our anchor." I have to admit, it's the changing nature of stars that makes me love them. A massive star that starts its life 10 times the size of the sun can end its life as an object only 2 times the mass of the sun, and collapsed all the way down to the radius of Manhattan Island. All that missing mass is still there, surrounding the stellar remnant as a large, colorful marker, saying something interesting happened here. The problem is, sometimes the leftover bits of one dead star superimpose themselves on the remnants of another dead star. And sometimes we just can't tell if we're seeing the chance alignment of 2 events or the stunning product of a single star putting on a show. The object HESS J1857 plus 026 was one of these "is it 2 things aligned?" curiosities in the sky. This single patch of sky is home to sources of gamma ray and radio light, and a young off-center pulsar. When things don't line up perfectly, it's easy to believe they may not all be in one place and actually associated with each other. To get to the bottom of this system, astronomers Alberto Percelli, Laura Duvadovich, and Elsa Giaccani imaged the system in a new color, or at least a different shade of radio light. This new data allowed them to determine there is a hot bubble, likely from the original supernova, and that hot bubble is the source of the gamma ray light, and the pulsar is inside the hot bubble. It's essentially a nesting doll of science. Not a well-stacked nesting doll, but there's a pulsar surrounded by a hot bubble, surrounded by a nebula, all shining chaotically in the night, and that is kind of awesome. Honestly, we are still finding wildly new objects as we explore the sky. Every time we turn on a new kind of telescope, boom, awesome new mystery. And some of those mysteries are super weird looking. In the first deep sky search for the brand new Australian Square Kilometre Array Pathfinder, or ASCAP, astronomers found what they are calling dancing ghosts. This discovery was released as part of a new radio map of the sky. According to lead researcher Ray Norris, when we first saw the dancing ghosts, we had no idea what they were. After weeks of work, we figured out we were seeing two host galaxies, about 1 billion light years away. In their centers are two supermassive black holes squirting out jets of electrons that are then bent into grotesque shapes by an intergalactic wind. There's still a lot to learn about this weird-looking system. But it's good to know it's not ghosts, and there is new science for people to explore. After the break, we'll be back to talk climate change, but then later in the program, we'll be discussing amazing stars in many different forms. Stay tuned. Back in early 2003, I came across an issue of either Science or Nature that had a theory paper in it on how changing the salinity of the Atlantic could cause the amazing currents in that body of water to just shut down. Right now, salty water heated in the tropics is circulated northward, and with it, it brings the energy necessary to allow the very northern British Isles to have a warm enough climate that there are palm trees. As that energy warms Northern Europe, Ireland, and the UK, the water sinks down and circles back toward the tropics along the bottom of the sea. It is the salty at the surface and less salty down deep density differences that allow this circulation pattern to exist. In that issue of either Science or Nature, they talked about how an influx of fresh water into the Atlantic could shut down that circulation and plunge those northern places into the cold. And later in the journal, there was an article on how the melting of Greenland's ice sheets was changing the Atlantic's salinity. At the time, people who love me took away my journals. They took away my general science journals. I could keep the astronomy ones. And they told me to just look toward the stars. But 20 years later, none of us can afford to simply be looking away. New research has shown that toward the end of the last ice age, a massive glacial lake burst and flooded the Atlantic with fresh water. This shut down the circulation pattern and plunged Europe into a 1,000-year ice age. Now data is showing that changing salinity is causing the current circulation to falter. And at any moment, the fresh water flowing off Greenland could be the final straw that ends this pattern. We are looking at a potential freezing of the northern latitudes while the tropics warm even more. And the average change might be just a degree or so. This is the hard part about averages. You can have massive changes at the extremes, and the middle only nudges a bit. We're already seeing some of the excessively high temperatures. The Mediterranean is baking, with temperatures in the hundreds of degrees Fahrenheit and 50s of degrees Celsius becoming a new norm for the first time, and wildfires sweeping through this region. New satellite images from Copernicus Sentinel-3 simply show a world of red where a variety of colors should map temperatures of all kinds across this mountainous region. There is at least one bright piece of science coming from a different study. The Climate Change Initiative Biomass Project is combining ground-based measurements with satellite imagery of the largest forests in the world. These are forests which sprawl across Russia's great western expanses. And this study finds the forests are doing more to store carbon than we thought. For several years, we've known that in general, there is increased vegetation productivity and tree cover. However, this work puts a number on that, and that number is 47% higher sequestration of carbon than previously thought. This study spanned from 1988 to 2014, and while the data for that period is good, the news for today is more troubled. Since then, fires have become more frequent, and dead trees can't transform carbon dioxide to oxygen, and smoke, well, the smoke of fires just changes things, not generally for the better. Folks, our individual footprints can't stop climate change. Most of the pollutants we worry about are coming from a handful of megacorporations. We still have voices, however, and we can sometimes influence those corporations to do better by our world and tell them to not look away. After the break, we're going to get off this planet and discuss stars being awesome. Stay tuned. Welcome back. And now for something completely different. I feel like we've reported on a lot of TESS stories lately, and that's actually unsurprising as the TESS Science Conference has been going on this week. I thought all the stories coming out would be about exoplanets, but it turns out the instruments on TESS are sensitive enough to collect all kinds of data about stars, not just exoplanet transits. In work presented at the conference, Mark Hahn gave an overview of a new all-sky map of red giant stars based on stellar measurements collected over the first 2 years of the TESS mission. The team was able to determine the masses and sizes of these stars across almost the entire sky, and in doing so, also measured the oscillations of the red giants, creating a symphony. The press release explains these oscillations by comparing them to sound waves made by everyday musical instruments such as guitars. When the string is plucked, it oscillates, and the sound waves can reflect, interact, amplify each other, or even cancel themselves out. The same thing basically happens in stars too, with hot gas rising, cooling, sinking, heating, and rising again. This process produces waves of pressure changes that act just like sound waves, interacting with each other and creating standing waves for minutes at a time that change the brightness of the stars. In our own sun, the changes would be on the order of parts per million. But with these red giants, the pulses happen more slowly, and the brightness change can be factors of 100 times or larger. Now, just as there are differences between the tones of guitar strings, violin strings, and even cello strings, so too are there differences between the pulses in red giants. These all depend on the size and mass, as well as other fundamental properties such as the interior structures of the stars. Stars like the Sun eventually expand out into red giants, increasing in diameter by a factor of 10 or more. And that larger size results in longer wavelengths and larger amplitudes within the atmosphere. Using TESS, we can observe millions of fainter, more numerous stars and measure their pulsations. During the primary mission of TESS, in those first 2 years, the spacecraft monitored about 75% of the sky, with each camera capturing a 24 by 24 degree image every 30 minutes. When the mission was extended last year, the pace of the image collection increased every 10 minutes. From these images, light curves were developed that measured the change in brightness of nearly 24 million stars over 27 days. That's how long TESS monitors any one section of the sky. And all of this is a lot of data. All that data was then analyzed using a machine learning algorithm that was trained using light curve data from 150,000 stars observed by the earlier Kepler mission. The TESS data turned up 158,505 pulsating red giants. Then the team used even more data from the Gaia mission, which gave them the distances to the stars. Once everything was put together and analyzed, the masses of the stars were plotted across the sky. The press release explains that stars more massive than the Sun evolve faster, becoming giants at younger ages. A fundamental prediction in galactic astronomy is that younger, higher mass stars should lie closer to the plane of the galaxy, which is marked by the high density of stars that create the glowing band of the Milky Way in the night sky. And co-author Daniel Huber sums up the work by saying, "Our map demonstrates for the first time empirically that this is indeed the case across nearly the whole sky. With the help of Gaia, TESS has now given us tickets to a red giant concert in the sky." There are some amazing videos and graphics, including a sonification of 3 different stars that we will link to in our show notes at dailyspace.org. The full paper will be published in the Astrophysical Journal. After another break, we'll be back with another TESS story, this one involving red dwarf stars and how their flares do or don't affect orbiting planets. Stay tuned. With last year's extension, TESS continues its mission, collecting vast amounts of stellar data and helping us discover even more exoplanets, all in the name of finding that elusive, habitable Earth 2.0, and maybe even extraterrestrial life. We all know that's the end game. And while red giant stars are amazing, they're also late-stage stars that have probably destroyed the nearest planets. Of far more interest to astrobiologists and SETI researchers are the more numerous and much smaller red dwarf stars. These stars can have planets much closer in, and the resulting dips in brightness due to transits is easier to measure as a result. Except that the hypothesis for years has been that any planets orbiting close in to a red dwarf will be sterilized by the superflares from the star. Superflares are extreme bursts of radiation. Our sun gives off flares as well, but because it's larger and older, the sun's flares are less frequent and less intense than those of the very young active red dwarfs, which is why scientists thought that life was unlikely on worlds around red dwarfs. Once again, enter the TESS spacecraft. Scientists at the Leibniz Institute for Astrophysics in Potsdam analyzed optical observations from TESS to understand just how and where these flares occur on the surface of the stars. What they found is good news for potential life in these systems. Graduate student and lead author Ekaterina Il explains, "We discovered that extremely large flares are launched from near the poles of red dwarf stars rather than from their equator, as is typically the case on the Sun. Exoplanets that orbit in the same plane as the equator of the star, like the planets in our own solar system, could therefore be largely protected from such superflares, as these are directed upwards or downwards out of the exoplanet system." This work, published in monthly notices of the Royal Astronomical Society, also provides more evidence that sunspots and flares tend to form close to the poles of fast-rotating stars like these red dwarfs. The team found over 3,000 red dwarf stars that had large flares recorded in the TESS observations. From those thousands of flares, they found 4 that worked with the analytical method they created, and those 4 stars had flares that occurred above 55 degrees latitude. That may seem like a very small data set, but the chances of finding 4 flares in a row at these latitudes is about 1 in 1,000, according to the press release. So maybe red dwarfs aren't such a bad place to look for biosignatures and technosignatures of alien civilizations. We'll be curious to see where this avenue of research goes from there. But for now, this has been The Daily Space. You can find more information on all our stories, including images, at thedailyspace.org. As always, we're here thanks to the donations of people like you. If you like our content, please consider joining our Patreon at patreon.com/CosmoQuestX.